Asteroid Impact. Earth has been struck by large objects throughout its history. The most recent extinction level event occurred 66 million years ago when an asteroid roughly 10 kilometers across hit what is now the Yucatan Peninsula. The impact released energy equivalent to 1 billion nuclear weapons, triggered global wildfires, and sent enough debris into the upper atmosphere to block sunlight for years. It killed approximately 3/4 of all species on Earth. An object 50 kilometers across would be enough to vaporize significant volumes of ocean water and generate a global fireball that leaves the surface largely sterile. Objects in the 100-kilometer range, which struck early Earth during the late heavy bombardment, could remove the oceans entirely. No confirmed extinction-level object is on a collision course, but the catalog of undiscovered near-Earth objects is not complete. Gamma ray burst. A gamma ray burst is the most energetic event known to occur in the universe. The most powerful type releases more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. If one occurred within a few thousand light years of Earth and its beam pointed directly at us, the gamma radiation would ionize the upper atmosphere in seconds, destroying the ozone layer and exposing the surface to lethal ultraviolet radiation. The hemisphere facing the burst would receive a dose capable of killing most complex life immediately. The opposite hemisphere would survive the initial pulse but lose its atmospheric protection for years. A burst at this distance is estimated to occur roughly once every few hundred million years. One may have contributed to the late Ordovician mass extinction 440 million years ago. Nearby supernova. When a massive star, within roughly 25 to 50 light years of Earth, exhausts its fuel and explodes, the resulting radiation and high-energy particles would pose an existential threat to life on the surface. The initial flash of X-rays and gamma rays would arrive at the speed of light and begin stripping away the ozone layer. Over the following years, cosmic rays from the expanding remnant would continue bombarding the surface, dramatically increasing mutation rates and cancer incidence across species. The combined effect would be a slow sterilization of the biosphere from above. No star within this danger zone is currently close to supernova. The nearest candidate, Betelgeuse, is roughly 700 light-years away. Magnetar Flare. A magnetar is a neutron star with a magnetic field roughly 1,000 trillion times stronger than Earth's. They occasionally release enormous bursts of energy called giant flares. In December 2004, a magnetar designated SGR 1806-20 released a flare so powerful it measurably ionized Earth's upper atmosphere from a distance of 50,000 light-years, briefly disrupting radio communications. If a magnetar of that power existed within a few light-years of Earth and released a comparable flare, it would strip away the ozone layer and expose the surface to lethal radiation levels within hours. No magnetar is close enough to pose this threat today, but magnetars are not always detectable before they flare. Rogue star passage. The sun moves through space, and the stars around it are not fixed. If a star passed within roughly 1 light-year of the sun, its gravitational influence would destabilize the Oort cloud, sending a cascade of comets into the inner solar system over hundreds of thousands of years. A passage within a few hundredths of a light-year would begin perturbing the orbits of the outer planets directly. Close enough, and Earth's orbit could be altered significantly, shifting it toward or away from the sun. Closer still, and Earth could be ejected from the solar system entirely, drifting into interstellar space. Stars are sparse enough that a dangerous close passage is unlikely in the sun's remaining lifetime, but not impossible over geological timescales. Rogue black hole. A stellar mass black hole drifting through the galaxy without a host system would be effectively invisible until it entered the solar system. Unlike a rogue star, it emits no light. If one passed through the inner solar system, its gravitational influence would alter every planetary orbit simultaneously. Earth could be flung outward into a frozen trajectory, pulled inward toward the sun, or ejected from the solar system entirely to drift as a rogue planet in interstellar space. The surface would become uninhabitable within decades as solar warmth faded with distance. Current estimates suggest the galactic density of free-floating black holes is low, but the total population is not directly observable and therefore unknown. Solar expansion. In approximately 5 billion years, the Sun will exhaust its core hydrogen and begin expanding into a red giant. Its outer layers will grow to roughly 200 times their current size. Current models disagree on whether Earth's orbit will be physically engulfed or whether it will drift outward as the Sun loses mass. Either way, the surface temperature of Earth will rise far beyond habitability long before the expansion reaches its maximum. Within approximately 1 billion years, increasing solar luminosity will drive a runaway greenhouse effect that boils away the oceans. Water molecules will be broken apart by ultraviolet radiation and lost to space. Earth's habitability ends billions of years before the planet itself does, before the Andromeda Collision. The Andromeda Galaxy is approaching the Milky Way at approximately 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will begin to merge. Despite both galaxies containing hundreds of billions of stars, the distances between individual stars are so large that direct stellar collisions will be rare. The danger to Earth is gravitational. As the two galaxies interact, the Sun may be flung into a different region of the merged system, or Earth's orbit may be destabilized by close stellar encounters during the process. The probability that Earth is ejected entirely from the solar system during the merger is estimated at roughly 12%. Vacuum decay. Current physics suggests the universe may exist in a metastable state called a false vacuum. If a quantum fluctuation were to nucleate a bubble of true vacuum anywhere in the universe, that bubble would expand outward at the speed of light. Inside the bubble, the fundamental constants of physics would be different. Everything the expanding wall passed through, matter, energy, and the structure of space itself, would be converted into a form incompatible with the existence of atoms, molecules, or any recognizable structure. There would be no warning. The bubble travels at the speed of light, so no signal could precede it. Earth would cease to exist in its current form in less than a microsecond after contact. Big Rip. If dark energy continues to increase in density, the expansion of the universe will eventually accelerate faster than any force can counteract. Every bound structure has a finite strength. Under sufficiently rapid expansion, galaxy clusters would be pulled apart, then individual galaxies, then solar systems, then planets, then molecules, then atoms. The Big Rip ends with even subatomic particles being torn apart by the expanding fabric of space. Current measurements of dark energy are consistent with a range of outcomes, and the Big Rip is not guaranteed by what we know. If it does occur, models place it approximately 20 billion years from now. Every structure in the universe ends at the same moment. Thanks for watching. Which topic would you like me to delve into next? Let me know in the comments. Also, please remember to like and subscribe if you enjoyed this video.